Hey everyone, and welcome to Module 1 of our Foundational Explainer series. Today, we are setting the stage for a massive shift in how we build software. To really get why this is such a big deal, let's just quickly ground ourselves. AI is the broad concept, right? Machine learning is how computers learn from data. Deep learning is where they kind of mimic the human brain, and LLMs, large language models, those are the specific text-based models we're all using today. But listen, we are moving way beyond basic ChatGPT usage here. We're not just typing a prompt and getting an isolated answer anymore. We're talking about building actual production-ready autonomous systems. So let's dive right in.
To really frame our whole discussion today, I want you to listen to this incredible insight from the researchers at Supermemory. They said the underlying models got good enough to reason through complex problems, but reasoning without the right context is just expensive hallucination. I mean, think about that for a second. Modern AI can finally reason, but its absolute lack of persistent memory? That is a fatal flaw when you're trying to deploy this stuff in the real world.
So here's our roadmap for fixing that exact flaw today. We're going to trace the agentic evolution, unpack the 4 core design patterns, diagnose what we call the memory bottleneck, map out the different types of AI memory, and then finally, we'll look at how to architect a real solution.
All right, starting off with part 1, the agentic evolution. We are literally witnessing a fundamental shift away from the super rigid software programming that we've all relied on for decades.
Let's just contrast the old way with the new way. Traditional automation runs on these very fixed, predictable rules. If X happens, then do Y. And hey, it's great for high-volume, repetitive tasks, but it breaks completely the very second it hits an exception. Agentic workflows, on the other hand, actually own a process end-to-end. They can handle variable, ambiguous goals. When an AI agent hits an exception, it doesn't just crash and burn. It reasons through it, it tweaks its approach, and it keeps pushing forward toward the goal. It's basically night and day.
Which brings us to part 2, the core design patterns. You might be wondering, how does this autonomous reasoning actually work under the hood? Well, there are really 4 core superpowers that let these agentic systems dynamically interact with the world around them. We've got reflection, tool use, planning, and multi-agent collaboration. Let's break down exactly what each of those looks like in action. In practice, reflection is exactly what it sounds like, the agent reviewing its own work. It's like a coder writing a script, getting an error code, reading that error, and then self-correcting without you having to intervene at all. Then there's tool use. This allows the agent to reach totally outside its training data to call live APIs and gather up-to-the-minute information. Planning is where the agent takes this massive, ambiguous goal and chops it up into logical, sequenced subtasks. And finally, multi-agent collaboration. That's where the system actually routes those specialized tasks between different agents to get the whole shebang done. Pretty wild, right?
But, and this is a big but, here is where we hit a massive brick wall. Moving on to part 3, the memory bottleneck. Let's look at what happens when these incredibly smart, reasoning agents have absolutely zero memory.
I want you to really think about this for a second. What happens when an AI literally can't remember yesterday? Or honestly, even what happened 5 minutes ago? Current large language models are, by default, fundamentally stateless. That means they treat every single interaction like it's happening for the very first time. For a real-world production deployment, that is catastrophic. It leads to 4 specific failure modes that will directly tank your operations.
The first major failure mode is what we call context poisoning. This is when an agent hallucinates, stores that hallucination as a fact, and then actually retrieves it later. Imagine a customer support agent hallucinates a made-up refund policy, logs it in the company system, and then confidently repeats that exact same error to every single user asked about it because it's now stuck in its context. The error just becomes a completely self-reinforcing loop. Next up is context distraction. So standard flat vector databases, they retrieve information based purely on word similarity, right? So if you ask an agent about an order status, it might retrieve 9 totally unrelated conversations just because the keywords happen to match. The actual signal you need gets completely buried under a mountain of irrelevant noise, and the LLM's attention span just gets diluted.
Then we have context clash. This happens when completely contradictory information gets loaded into the agent's brain at the exact same time. Let's say a user updated their shipping address, like a week ago. If the system retrieves both the old address and the new address with similar relevance scores, the agent gets super confused. It doesn't know which one is the current truth, which just leads to wildly inconsistent and unpredictable behavior. And finally, work duplication. In a multi-agent system where they don't share any state awareness,
Agent A might fetch a user's transaction history, and then literally 10 seconds later, Agent B goes and fetches the exact same history all over again. It is incredibly frustrating to see this massive computational waste, not to mention your token costs are going to completely soar simply because these isolated agents aren't talking to each other and sharing what they've learned. Okay, so how do we actually fix this mess? That brings us to part 4, types of AI memory. It turns out, by mapping AI architecture directly back to how the human brain functions, we can find the exact structural solution we need. So there's a really vital distinction between two primary types of memory here. First, there's parametric memory. This is the stuff baked directly into the model's weights during its training. It's super powerful, but it's rigid, it's opaque, and it is incredibly expensive to update. Contextual memory, however, is external. It's flexible, you can update it instantly via retrieval without having to retrain the entire model, and it's effectively unbounded. To build reliable agents, mastering this external contextual memory is absolutely non-negotiable. We can actually break that contextual memory down even further by mapping human psychological memory directly to AI data structures. It's really cool. Working memory, that's just the LLM's active context window. It's fast, but super limited. Episodic memory tracks history across different sessions, so it remembers who you are today based on what you talked about yesterday. Semantic memory is the factual knowledge base, tracking absolute objective truths about the world, and procedural memory encodes learned skills, meaning the agent doesn't have to relearn how to do a complex task every single time you ask it to do it. Understanding those memory types is step 1. Step 2 is our final section, architecting advanced memory. Let's dive into the actual structural architectures required to fix this bottleneck in production. First things first, we absolutely have to move away from flat vector storage. Flat storage searches through everything all at once, which, as we talked about, leads to massive noise and context distraction. Instead, we need hierarchical graph retrieval. Think of it exactly like a giant filing cabinet. Hierarchical systems route information efficiently through layers, like you check the right drawer before you start checking specific folders, rather than exhaustively scanning millions of flat records at once. It gives you incredibly precise recall, even at scale. And to really power that retrieval, researchers are looking at the Zettelkasten method. This is essentially a dynamic, smart notebook for the AI made of interconnected atomic notes. Whenever an AI agent has a new experience, it autonomously generates a comprehensive little note about it. It then analyzes and links this new memory to historical ones, based on shared tags and attributes. So the memory network continuously evolves over time, which ensures multi-hop factual exactness. This all builds into what researchers are calling active dreaming memory, or ADM, which actually relates AI memory consolidation directly to human sleep. It's wild. During the wake phase, the online agent is just interacting with its environment, simply storing raw episodic traces of its successes and failures without even trying to process them yet. The real magic happens offline, during the sleep phase. The system takes all those raw failures from the day, clusters them together, and abstracts a brand new rule. Then, incredibly, it literally dreams up counterfactual test scenarios in a secure sandbox to verify these new procedural rules. It basically asks itself, hey, would this rule work in a slightly different scenario? If yes, it gets stored as verified semantic knowledge. This is exactly how you enable true lifelong learning in an AI. But, a truly efficient brain also knows how to forget. Actually, selective forgetting is a completely critical piece of the architecture. By using a formula based on recency, relevance, and frequency, the system actively prunes low-value data. Forgetting isn't a bug, it's a strategic resource. It keeps your retrieval clean, it stops context distraction in its tracks, and it drastically cuts down on those crazy token costs of running agents at scale. All right, let's wrap this all up. You are now equipped to see exactly why agentic workflows are replacing brittle automation. They own tasks end-to-end through reflection, tool use, planning, and collaboration. But for your agents to actually work in production, you absolutely must treat memory as core infrastructure. That means moving way past flat databases to hierarchical routing, active dreaming, and strategic forgetting. Which leads us with this final, absolutely crucial thought for your own system deployments. Your agent can reason, but can it remember? Because if it can't, it's not really an agent, it's just an expensive hallucination. Thank you so much for joining me in this explainer today. Keep learning, keep building, and I will catch you in the next one.